Also learned in our last video that there were some problems with the Bohr model. It didn't work for anything but hydrogen. So let's talk about what our current model is. So the Bohr model was a big step forward, but it was only useful predicting the frequency of the spectral lines for atoms that had only one atom, which is pretty much hydrogen, or some ionized atoms. We'll get into those later, but it had to have one electron. So that the idea that the electron was a particle in orbit around the nucleus, but with wave-like properties that only allowed for certain unique orbits, it only worked for hydrogen. So semi-classical explanations failed except for hydrogen. So it turned out that only a lucky chance that it let it work even in that case, because we really did not understand what was going on until a couple of years later. There were some physicists and scientists and chemists and such were discovering the field of quantum mechanics. Now, quantum mechanics is a branch of physics, and it provides a mathematical explanation of wave-particle duality. And it successfully explains the following two ideas. So, energy states in complex atoms and molecules, and the relative brightness of the spectral lines. Now, it's widely accepted as being a fundamental theory underlying all physical processes even now. It's our most current theory that we have as far as stuff. So, was it a particle or was it a wave? Well, that's what we're going to find out. The goal was to explain why electrons in an atom don't fall into the nucleus. That's what we started with all this, right? So an electron, as a charged particle, would fall in because of Newton's second law, F equal mass times acceleration. So taking into account that light exhibits properties of both a particle and a wave, in 1924, French physicist de-Broglie asked, if light can behave like a wave or a particle, can matter also behave like a wave? Amazingly, it does. So de-Broglie proposed that matter might also behave like a wave and have a wavelength associated with its momentum and its mass. So he earned a Nobel Prize for a real simple derivation of recent discoveries about energy and matter. Pretty much what he did was he set Einstein's formula for relating energy and matter, E equal mc squared, equal to Max Planck's formula relating energy and the frequency of a wave. So what he did was took E equal mc squared. Now notice he substituted v squared, or velocity, because, well, real particles really don't travel at the speed of light. So he was able to do that, and he made those equal. He substituted mc squared, or mv squared, for E into hf, and this is what he got. So mv squared equal hf. He substituted the wave formula, all right, in for the frequency. Okay, he had for the v, it was c, right, because we had c equals lambda times frequency. So it was hv, or hc, over lambda equal mv squared, because of this. Frequency equals c, or v in this instance, divided by lambda. So he divided through, he factored out v, right? So now he's got mv equal h over lambda, max constants. So now he found that lambda, or the wavelength, equals Planck's constants divided by mass times speed, or velocity. Okay. So the de-Broglie hypothesis that particles have wave-like properties needed to be supported by an experiment. So, again, a Nobel Prize winning experiment. Davison and Germer of Bell Labs found that electrons could be diffracted, all right, just like light waves. So what they did is they shot a little electron gun, all right, through this double slit, and this shows the interference pattern where these electrons were deflected. So they acted like a wave. And we'll see the video in class tomorrow of what goes on with this double slit experiment. So this is what they saw. These are the actual photos, and the photos of electrons being fired one at a time through the two slits. Each exposure was made a slightly longer time. So the same pattern emerges as was found by light. This is what it looks like with light. So each individual electron has to behave like a wave and pass through both slits. But each electron must also be a particle when it strikes the film, or it wouldn't make one dot on the film. It would be spread out. So this picture right here, these pictures show that matter acts like both a wave and a particle, or it showed the wave particle duality of electrons. Fascinating, right? So what is the wavelength of a 0.25 kilogram ball? That's its mass traveling at 20 meters per second. Let's pull out my little formula sheet right here. Wrong one right there. Okay, I want to have my little formula sheet so I can do these things. So, let's see, I got a mass. Mass. I have to switch off there, so let's see, control 2. I got to turn off this. I got to turn off my blue thing. So I've got mass equals 0.25 kilograms, and I've gotten a mess right there. Let's pause and I'll come fix this and be right back. Okay, let's remember something. Okay, let's remember, if I'm a pen, on one of the previous slides that we had, let's see, lambda equal h over mv. Okay, h over mv. So lambda, we're trying to find the wavelength. We know the mass, and we know the velocity, 20 meters per second. So oh look, we've got h right there, and by the way, that's a joule. Okay, let's see. So lambda equals 6.63 times 10 to the minus 34th kilograms meter squares per second over 0.255 kilograms, that's 5, times 20 meters per second. All right, and let's see if we divide it through all this out. All right, that'll give us meters. So let's see what we get. All right, so I've got 6.63 to the minus 34 divided by parentheses 0.25 times 20. I get 1.326 times 10 to the minus 34th meters. So that would be the wavelength. And then we could look at it in nanometers and figure it all out. What's the wavelength of an 80 kilogram person running 4 meters per second? Well, now we're just using the formula and subbing it in. Of course, we remember it's h times mv. We have h right there. We have mass and we have velocity. So lambda will be what? Maybe it'll come out 6.63 times 10 to the minus 34th kilogram meters squared per second divided by 80 kilograms times 4 meters per second. Let's see what we get. All right, 6.63 times 10 to the minus 34. Whoops. 34 divided by 80 times 4. And that's going to be, I got 2.07 times 10 to the minus 36 meters. That's what it is. Let's see what else we got. What's the wavelength of the matter wave associated with an electron? All right, and the mass of the electron is that, moving with a speed of 2.5 times 10 to the 7th meters per second. All right, so same formula, just different numbers. All right, H over mv. Lambda equals 6.63. I've got just some more keys to punch, but essentially it's the same problem. All right, divided by what mass is 9.1 times 10 to the minus 31 kilogram times what? 2.5 times 10 to the 7th meters per second. So let's do our math, our arithmetic to get our answer. And this is all this is, just simple arithmetic now. Divided by 0.1 times 10. 10 to the minus 31 times 2.5 times 10 to the 7th, and that should give me 1.51 times 10 to the minus 56 meters. Okay, very, very, very small number. What's the wavelength? Well, we just did that one. Okay, guys. So, some other people were studying this, right? They were studying this, and it wasn't just all good. They were learning more, and we were learning more about the atom. So the Bohr model, of course, of the atom holds that electrons in specific energy levels and locations around the nucleus of an atom. So quantum mechanics tells us a little different, that there are inherent limits to measurement of the position and momentum of an electron around the atom. Okay. Now, this is not because of our instruments, but it's due to the wave-particle duality and to the interaction between the observing equipment and the object being observed. Okay, essentially, if I look at the electron, I hit it with a photon, and that photon is going to move the electron. So I can't know the position, okay, and the momentum of the electron at the same time. I can do one or the other. So if I was going to look to the most powerful microscope, one that's not even invented yet, all right, when I look through it, that photon is going to hit the electron, and it's going to go to the microscope. When it does, it's going to transfer its momentum to the electrons. All right? So it's going to change its position. Electrons are so small that the very act of just looking at the position changes their position. All right? Think about this. If you were in a large, dark warehouse, big warehouse, and there's a bunch of marbles rolling around on the floor. You can't see, and you can't hear, and you're giving a walking stick to locate the position of the marbles. You got to count all those marbles. So what would happen, dark room, every time you try to measure or point or hit one of the positions of the marble? Well, let's ignore friction just for fun and allow the marbles, they can fly around the room in 3 dimensions. And that's what electrons do. Could we ever really know where the marble is exactly? No, we couldn't. So what Heisenberg postulated is that there was a limit to how accurately you can simultaneously know both the position and the motion of the particle. No matter how good, how wing-ding fantastic your measurement instrument is, the more accurately you know the position of a particle, of the electron, the less likely you can describe its momentum, and vice versa. So, and that's ruled by this little experiment here. So this is called the uncertainty principle, Heisenberg uncertainty principle. The result of this uncertainty is to limit the outcomes of an experiment. For example, a quantum transition between 2 states of an atom always results in the emission of a photon of a very specific energy. So the idea that the position and momentum of an electron cannot be measured with infinite precision is referred to as what? Pause, and it would be the uncertainty principle, Heisenberg's uncertainty principle. If the accuracy in measuring the position of a particle increases, what does the accuracy in measuring its momentum will do what? Increase, decrease, remain the same. If you don't believe me, you can look, but it'll decrease. So, about done. As Heisenberg was doing his work, Schrödinger was also working on a mathematical model that would describe the behavior of an electron around that atom. So, he said, let's treat the electron as if it was a wave. So Schrödinger's wave equation describes the most probable position of an electron in terms of its wave function. So Schrödinger received the Nobel Prize in Physics in 1933. That was less than 100 years ago. It was like 91 or 89 years ago for the development of the Schrödinger equation. So, don't expect you to totally understand this. Heck, I don't totally understand it myself. But the wave function, psi, and that's what that is, describes the state and behavior of the electron. So let's look at this little GIF right here. The 2 fields of the wave are noted in blue and red in this GIF animation. So each wave frequency is proportional to the possible energy of the oscillator. That's the thing that moves up and down. So each wave function is also associated with a set of 4 quantum numbers, which we'll go into later, which accurately describe the energy and the most probable location of an electron of any atom. Not a for sure location, but the probable location. So, in classical physics, predictions about how objects respond to forces are based on Newton's second law, F equal ma, or force equal mass times acceleration. In quantum physics, this doesn't work. So predictions are based on the Schrödinger wave equation. H psi equal E psi. H is the Hamiltonian operator. All right. Psi is the wave function. E is the energy. Okay. Don't have to worry about memorizing that. Thank God. So, quantum mechanics provides a mathematical definition for what? The wave-like properties of electrons, the particle-like properties of electrons, the classic Newtonian forces that govern atoms, or the wave-particle duality of electrons. Pause, and hopefully you guys stated D. the wave-particle duality of the electrons. So quantum mechanics, less than 100 years ago, was formulated, is the basis for what stuff is. It explains, it's our most current model, and we're still exploring it. But quantum mechanics, so we're going to spend the next couple of days talking about what quantum mechanics are, the quantum numbers, the quantum shapes, and the probable locations of where each specific